All right, so welcome to our second meeting at San Francisco Dynamo User Group. We have an exciting presentation today. We have Dr. Glenn Katz from Stanford and Mohammed Als talking about going beyond parametrics and using optimization workflows utilizing Dynamo. A couple of things before we get started. Restrooms. The restrooms are down the hall on the left and then to the right by the elevator hall. In the case of an emergency, you see the three exit signs. There are two, there's on the north and the east and the west side. And the other thing is we just finalized setting up the structure of the group. We are still meeting once a month. We are working really hard on bringing you the best speakers around. Just to remind you, the format of the meeting is to have a short learning module followed by a case study presentation, which is the main topic for the meeting. The place by default is HOK. I'm trying to set this out as a rotating meeting where we can switch the venue. In case there's not available venue, then we could, by default, do it here. So if you're open and willing to share a space that can hold about 50, 60 people, come forward. We're happy to switch it over. The other thing I want to really I appreciate the sponsorship of Ideate. They provided the food for this session, and they will be working with us in future sessions as well. So now we have a committee. Last meeting it was just one person, and now we have 6 volunteers who are stepping up to work in this for this meeting. So we have Glenn Katz from Stanford, if you can just raise a hand. Sue Young from SOM. Oh, my apologies. I'll fix that. Christopher Crowley, not here. Okay, AECOM, Colin from Autodesk, Brock with the Rufus, and me, coordinator. So we have, as a reminder, we have a website. All the meetings announcements will be done in there, and from there you can register. We tested for the first time doing the invitations using Eventbrite. It works pretty good. It enabled me to have the list of attendees in a more streamlined way. What I'm going to change is the ability to register only 1 ticket per person, because I had one person who reserved 20 tickets, and then he canceled. So if you want to reserve, it's going to be on an individual basis. You can forward this to whoever coworkers want to come in, but I just need 1 person per email. And any questions, that is the email of the group, San Francisco Dynamo User Group Coordinator @gmail.com. Some announcements. We are working to finalize the lineup for the rest of the year, and we have 2 confirmations. For October, we're going to have Adam Sheether as a virtual presenter from JTL in Malaysia. And in November, we're going to have Havard Vasau with Soneta. You know him. He's a really renowned speaker, and he's doing great things with Dynamo and computational design for structure. He's also going to be joining us remotely and presenting what he's been lately up to.
And that one's going to have a different time, right?
That's correct. So because he's in Norway, the November meeting is going to be at lunchtime. So hopefully some of you can make it. Lastly, that's it. So welcome Mohammed Als and Glenn Katz, and the stage is yours. make you the presenter, and then you could switch or accept be the presenter.
Okay. Hello, everyone. I'm Mohammed, and I'm going to talk about Optimo today. I created Optimo as part of my research when I was doing my PhD at Texas A&M University, and later I made it open source and available for everyone to use it on Dynamo. So I will go over a little bit about background of optimization for those people who are not familiar with especially genetic algorithm, the way it works. It's better to have some understanding before starting playing with Dynamo. So I will cover that part first, and then I will go ahead into Dynamo and show you a few examples that comes with with Optimo when you install the package. And after that, Glenn has a lot of cool examples to show you using Optimo. Okay, I had another image myself, so I put the first one for this session. And this is the case study that I've done with for optimization of building energy performance. So it's a multi-objective optimization. This is like a Revit sample file, but the whole idea is optimizing. Is it me or it's not my machine? Really?
It is, yeah, here. Started it.
Is it? Huh? Okay. Was it mine?
If you touch the screen, it's a touch screen, so it may have done something.
Okay. Yeah. So I stay here.
Everybody gets it.
Yep. So in this case, the goal was minimizing the energy performance of the building and maximizing the daylighting in the building. I don't talk too much detail on this example. It takes some time and it needs familiarity with Dynamo daylighting analysis and also energy analysis. But I had the photo here just to show you you can go deeper than what we are showing here. Okay, so I'm working. I finished my PhD this summer, and I'm working as a building performance analyst with Autodesk. I did my undergrad in civil engineering and master in construction and PhD in architecture. So the full range of AEC is covered. Yeah. Okay. So going back to the topic, the whole engine for Optimo right now is genetic algorithm. It's using multi-objective, so it's called NSGA. I will talk about that, but there is an option to add more algorithm if someone is interested. It's open source. If you think you have something that you want to add to it, you can go ahead and download the source code and add to it, and if you want, you can share it with other people. So here I just talk about genetic algorithm and a little bit, and show a very simple example about the background of it, and then showing it into Dynamo. So genetic algorithm is a heuristic method that uses natural evolution concept for optimization. It uses natural evolution process such as selection, crossover, mutation that you see in natural evolution to come up with the optimized solution. Also, genetic algorithm is good for exploring the design space. So it's not just you can use it for exploring a design space, and it's not just good for optimizing a solution. When you have like a wide space that you cannot predict how the design space would react, you can use genetic algorithm to explore the design space that most of the time it's not easy for humankind to explore. So let's just go quickly about the background of GA. GA starts with a population of randomly generated samples. So let's say for this case that you will see more detail of this case later in Dynamo. But for this case, it's a surface. Let's say you want to find the the lowest position of this surface on this automatically with optimization process. So the goal is to optimize the function to find the minimum z-value of this surface. So this is the goal that you define. For optimization, you need to have your goal clear first, and then you need to create the whole workflow to achieve that goal. So in this case, what we do is to design the optimization process, we need to have X and Y as an input or random generated items for the process. And then we need to use those X and Y randomly generated to come up with the, to get the Z values. So here, let's say these points on the XY surface are randomly generated. So this is the very first step in optimization process. You create a random generation of a few samples. So here, like random X, random Y, it gives you a point on the XY surface, and then you use those points and project like towards Z direction to find the intersection with this surface. After finding the intersection with this surface, you get the points on this surface. So for each sample that you created, you will get a function result back from this process. So in this way, I'm just showing you that for different problems, you need to come up with a solution like this. You come up with a way to get your function back. Here, we are randomly generating X and Y. We are shooting rays towards Z direction, find the intersection with the surface, and read that the Z value of the intersection. So the Z value would be outcome of the function that we are looking at. And this would be the points that we are getting. So overall, we could see that we generated a randomly populated samples first. Then we calculated the fitness function. The Z value, the fitness function is the function that you are trying to do optimization over. So we calculated the Z value here as a fitness function. So in the next steps, step by step, we try to improve the values in the process. So it goes through iteration, and in each iteration, the solutions would be improved. So we are using selection, crossover, and mutation in this process. I will show you a very simple example of selection, crossover, and mutation here, just to get a better understanding of how it works. So just assume that we created about 10 randomly generated X and Y. Then we shooted arrays from these X and Ys and got the Z values on the surface. So these are the randomly generated points on this surface. You can see them, they're all over this surface. Then what we do is we sort these. So because we are looking for the minimum Z value, we sort them from lowest to highest. And we give them the higher chance for those that are fitting our fitness function more to be selected. So here the top two, or the top one has the highest chance to be selected, then the second one, and so on. So here, let's say we randomly go and select a few of these out. Here, let's say the first two are selected. This is the selection part. So you're sorting them, you're giving them the higher chance for the better ones to be selected. This is the selection part. Then it comes to crossover. The crossover is like you're combining two good solutions to come up with a better solution. Here, just follow the colors, green and the green one and the yellow one. For the next round, we just switch the position of X and Y to come up with different solutions. So we can see that we created two new solutions, and we calculated the Z value. One of these Z values are good results, 16.3, which goes here. It goes as a second solution for us. So we come up with a good solution by just randomly changing some of the features of our previous solution. 43.6 is not that good, but in the next steps it will go out of our solution process. And we have one more concept in optimization process called mutation. And for mutation, one gene, every solution we can call them gene. One gene is selected and randomly changed to different things. Here, let's say we switch the positions and we change this one, or randomly change one of these solutions out. So we can it's like mutating through the one simple solution. This is another way in the process of optimization to not get into the local solutions. We want to go globally and find the best solution. There are other ways to do mutation I don't want to go over. So having this quick background, just get ourselves familiar with optimization jargons. I'll go and talk about Optimo a little bit. So this is a genetic algorithm for multi-objective optimization in Dynamo, and it's using non-dominated sorting genetic algorithm. I don't want to go into detail for that. I give you some hints where you can find more information. The first thing is the source code of the Optimo is available on GitHub. You can go ahead and look if you are interested into details. And we have a website that I didn't introduce it to many before in any other places, but we are trying to keep it updated. You can go there. You can see some video tutorials. You can see some other research that's been done using this. Maybe the most useful part for you would be the getting started videos. There are 3. Okay, there are 3 videos that about like 10 minutes each. Starts from very simple example to a little more complex examples that shows how to start creating the whole graph for optimization. I think the link to this website is sent out in the invitation email if you want to look at it later. Okay, so before going to the Dynamo and show you how it works, just keep in mind for each optimization process, we choose parameters to optimize first. So the same as the example we showed, X and Y would be 2 parameters that we change for optimization process. We determine the correct representation of the parameters. So here would be again like we are using points. We generate solution, we evaluate the fitness function, and then we put them in a loop. So we are going to create the same process in optimization process. The first example, I'm going to this to Dynamo and show you the example that I explained here. So let me open Dynamo. One good thing about the Optimo package is since it's not using anything related to Revit, it doesn't need any change from my side to have it updated with new versions of Dynamo. So automatically, any version of Dynamo you have, you can use Optimo. It doesn't need any change. Today I downloaded the latest build of Dynamo, and I tried it, and it's working. So there is no problem even with the ones that are daily with it. So
I'm worried.
And, don't worry about that. Here is the graph of optimization that you can see here. Each graph has like 2 or 3 or 4 main parts. You can see it here. The first part on the left side would be the user inputs. All the user inputs are here, and the middle part would be calculating the fitness function, and there would be a loop. This is the loop node. It's shipped with Dynamo. You can use it for other loopings in Dynamo, and at the end you can export the results. So 3 or 4 steps, you can up to you how you want to think about it. You can have the optimization workflow, and this is the same thing with all the examples that I have as examples that comes with Optimo. So first we go to the left side of the chart, the user inputs. The first thing we need to define the population size. We said that each optimization process comes up with a randomly generated samples. You need to say like how many samples you want to create. You want to create 100, for this case 100 points, 200 points, 400 points, whatever you want, you provide it here. The second one would be number of objectives. This is the case because we have a multi-objective optimization algorithm. You need to make clear for the optimization process how many objectives you have. here, because we are trying to optimize the Z value, there is just one objective. I inserted one here. If you have more than that, like in a case that we are doing daylighting and energy, it does two fitness functions. I put 2 here. And the next thing would be defining the lower limits and upper limits for each item that you're generating. So for this case, you define where do you want the randomly generated points to be. We don't want to just put it all over the place. That's wasting your time. You want, if you have enough knowledge about what you're doing, you can limit it to get a better solution faster. So here, because I know the orientation of the surface that I have, I just put from 0 to 300. So all the points are generated randomly from 0 to 300. And these are the built-in list nodes that comes with Dynamo. You can use those. The reason that I have 2 items in this list is because I have X value and Y value in the process. So each point that I define in the XY surface needs the X value and Y value. So I say X would be between 0 and 300, and Y would be between 0 and 300. And here is the fitness function part that you define for your optimization process. I'll go into detail for this in a bit, and then let's assume that we know how this part works, the fitness function. We come up, this node generates that random population. So if I, just to be a little quick here, let me reduce the number of rounds to 6, number of points, because I want to show the list here. So this comes up with a list of 3 lists in it. The reason that we have 3 lists in this node is we have 2 variables that we are changing, X and Y, and we have one fitness function, which is the Z. And you can see all the Z values here still 0 because we didn't do the fitness function calculation. So if we do the calculation, this list also will have some numbers in it. So here, just to know, these 2 numbers are X and Y, and the Z would be calculated here, and the result, you will see it here. And if I show you the fitness function values, these values would be the Z values. And this node combines these 2, just copies these values instead of the Z values here for you.
Can you zoom in a little bit, Mohammed?
Zoom in, yeah.
You can do it. You can do it.
This is scary.
Whoa.
Okay, so let me zoom out myself here. Okay. Okay. So,
It's like an iPad.
yeah, huge iPad.
iPad Pro.
Yeah. So.
Pro S.
So. Okay.
Yeah, sure.
So this, when you have the assign fitness function, you created the randomly generated list, then you calculated the fitness function, and this node just combines these 2 lists. It looks fancy, but it's just combining 2 lists together. It's overwriting these zeros here in this list. So at the end of, till here, we will have 1 randomly generated samples and calculated the fitness function for them. So let's say we stop here and going back to see how the fitness functions are calculated. Who is familiar with how functions work in Dynamo? It's a little complex feature, and it's something that Dynamo is. I think it's a strength of Dynamo over Grasshopper, because you cannot have you cannot move in the wrong direction in Grasshopper. You cannot go from right to left in Grasshopper. Everything flows this way. But in Dynamo, sometimes you can go right to left, and sometimes you can go left to right. So this function, having functions, give you the chance to go from right to left. And the way it works is when you have a node and you don't have input to it, and you connect that node to some of the nodes in Dynamo, like function.apply, list.map, or a few other ones. You can use them as a function holding nodes. And the way that it works here is I'm missing this population list input here, and so it makes this node act as a function. And when it's missing one input, later it's connected to function.apply. The function.apply gets a function which we have here, and it gets a list of arguments. So it gets this. It gets the output of this as an input. What it does is it applies this list. This applies this function to the list that it's submitted to it. It's a little complex, but just think about it in a way that you have a list, you have a function. The function.apply applies that function to that list. You want to add anything to it?
It's really hard to describe. Yeah, you have to play with it.
Yeah, if you play with it, I would say you can get it right away, but explaining it is a little difficult. So this is my fitness function, and the reason that I did it as a function and I didn't do it in a straightforward way is because later what you do is you replace your fitness function, whatever function that you have, delete these nodes and put it there, and it works properly. So the main problem in optimization workflows is most of the time the fitness function is hard-coded in the optimization workflow, so you cannot go ahead and make changes to it. Here it makes it open, so you can import your fitness function here in the process.
So, Mohammed, if I could just say that another way, it could be like that function node on the bottom left corner there, that's kind of like the lighter gray color.
Yeah.
You could take this example file and use a different custom node that you define yourself,
Right.
plug that in, and it
Yeah.
would work for your function.
Right. So what it does here is it finds the point, the z-value on the surface. So you can replace it with something like finding the structural performance of a structure file in Revit. So it can be very complex. Here is a simple project, but you can replace this with a more complex process. I think Glenn has he will show some cool examples later on this. But let me open this. It's a custom node, and what it does is it's just HOK people finger.
There you go.
Okay, I inserted my fingerprint. So this custom node does exactly the same thing that I showed in the PowerPoint presentation. So what it does is it gets those X and Y for each point. It shoots a ray. You can see it says line by start point and direction. So it shoots those lines that I was showing in the presentation, finds the intersection with the surface, and gets the z-value. So very simple function, but just assume that you can replace this function with a very complex function that you have for your project. So it returns the z-values here out of this function. So the next thing is you need to know is every time you have a function, even you have one function, you need to add it to a list node. And the reason is because I put this one, so later if you have more functions in your project, you can easily add lists and copy your custom nodes here and insert it, and it automatically do that. Just remember that the number of inputs here and this number of objectives should be matching. So you can have one here and two here, but it's not going to work. And so after having the first population generated, so half of the work is done. From your side, almost all of the work is done, because everything else is automatically used for calculating the loop as well. But I will explain how it works. Here is our first generation for optimization process. The next would be putting this process in a loop that improves the result step by step. So We have a loop function, a loop node here. Loop node is one of those nodes that I talked about, that it can handle functions. It's the same as function.apply or list.map in Dynamo. The way it works is it gets a function, which would be this NSGA function. NSGA function is just, NSGA is the optimization algorithm name, and the reason that's function is it's missing one input. And it gets another function which is called loop completion check. It checks, like, you put a number here and it checks if the loop is iterated that many numbers. Here I just put it 1 to be faster to demo it to you. You can have it 50, and this loop node checks if the counter is smaller than this number that you input here, it continues iterating through the loop. So you have 10, it iterates 10 times and stops after that. Let me increase this to, where is my, yeah. Okay, it doesn't show the surface. Okay, it doesn't matter. So what did do this to?
Can you right click on the show surface?
This one?
On the left, the select surface.
This one?
Yeah.
It's pretty on. Yeah, it was showing it. I don't know what happened. Okay. You just need to imagine it from here. Let me go and. I can open it again.
Yeah, daily build, dude.
Yeah. So yeah, I was because I didn't have the other versions of my machine. I just downloaded the latest build. But just assume that the surface is here, and these are the nodes on the top of that surface. Because we are just doing this iteration, let me do one time. So if I'm doing it one time, you see all these points are all over the space, and the more that I increase the loop, they're getting focused and they're trying to find up, like they're crowding around one point. So it's if you remember the surface, let me show it here. The surface has two local minimum here, and one global minimum here. So these points are exactly the same as process that I have here. You see, they're like this process. I'm showing it in Dynamo right now. They start gathering on the minimums, and when they found that this is a local minimum and this is the lowest point on the surface, they start getting gathered in this part of the surface. So I'm just showing the same thing in Dynamo, but because the surface is not showing up, it's a little harder to imagine. But if I do 10 rounds, yeah, you see all the points are gathering here after 10 rounds. It seems that it's finding the optimum solution here. We understood that how the loop while node does two functions, and this is the counter. This is the input. What it does is we have this list as the list of sample randomly generated items, and this is a counter. I say start from 1 and count and add 1 to it, so the next time would be 2, the next time would be 3, and compares the result with this 10, and when it gets to 10 it stops. So this is a counter, nothing to worry about. And in NSGA function we have a few more things, but it does exactly the same thing that we did for creating sample random generation at the first. The only difference is instead of having the node initial generation over there outside the node, it has generation algorithm which improves the solution. This is in the source code. You don't see what's going on inside here, but it's the exactly same process that I explained in the presentation. So you get the first random generation here. This node improves the result. You calculate the fitness function, and it spits out this result. it goes to the loop again, uses the new randomly generated functions, which are better this time, and comes in and it does and iterates through this, and every step it improves the solutions. So this is the loop that improves the whole generation process for you. And how much time?
We're 5 minutes overhead.
Really?
So if you-
Okay, so I have 5 more minutes, right? Okay, I'll wrap it up. And at the end, it's like very simple thing. I have here just points to show the points on the screen. You don't need to have this, and this is exporting the result to a CSV file. And very quickly, I just want to talk about multiple objective. One of the very famous multiple objective problems in optimization is having two functions, two mathematical functions. One is x to the power of 2 and the other one x minus 2 to the power of 2. This is the way these charts look. And by changing our parameter would be x. So by changing the x in this direction, we want to find the minimum value for both x to the power of 2 and x minus to the power of 2. So just by looking at it very quickly, you will understand if you select a point here like in minus 2, minus 2 to the power of 2 would be 4, which is and minus 2 to the power of 2 would be 16. So this is one value. If you go to 0, the first one would be 0, the second one would be 4. So 0 is a better solution. And anything above, beyond 2 would be a larger solution. So you can see that your solution can be between 0 and 2, but by looking at it, you cannot come up with the best solution that minimizes both functions. When you move from here and going toward this direction, the first function is increasing, the second one is decreasing, and when you get to here and you're increasing the first function more and decreasing the second function, and when you move toward the other direction, the reverse happens. But there is no point that you say this is the best direction, the point for me to select. At this point, because you have two conflicting objectives, you need to come up. You need to have a set of solutions, which is in process of design is more ideal because you give a set of solutions to the designer and he can choose based on other specifications of the project in the process. I will show you a better example in optimizing daylighting and energy, but just having this a quick example here, you can the same thing that I explained, and at the end it would be this range of solution would be best solutions for you. This is 0 from 0 to 2, and at one point one of the function is 4, at the other point the other function would be 4. And the only way, the only difference that you have in Dynamo is, let me open the, it's called, the problem is called SCH problem. The only thing that you need to change in Dynamo is the first part. You're changing the number of objectives to 2 this time, and you're having 2 fitness functions. And these fitness functions are very simple. It's like getting the x value and doing a power function, x to the power of 2, and the other one is x minus 2 to the power of 2. Very simple mathematical function. You import this, and the whole process would be exactly the same for optimization. So you could see that it's very easy to jump from one objective to 2 objectives and from one fitness function to other fitness function. Because I'm over time, there are videos for each of these examples that comes with with Optimo. There is a video on that website that I showed you. You can have a look to it. Just let me quickly give you an example on optimizing the 2 objectives in building design. Let's say these are the windows that we want to try to find the optimum size for these windows to have the lower amount of energy for this side of the building and having the most daylighting values here. So what you do is you see when it gets to this like a real project or a real example, the chart gets more complex. So more inputs as items for optimization process. Like I have the size of the window, the thermal properties of the window, or other specifications of the window as an input. And the same process, and for fitness function, it would be energy performance, and it would be daylighting performance. And so it looks, it's a little slow, but you can see like it would look like at the end something like this, that the window sizes are changing, and it's finding the optimum solution based on the energy and daylighting performance. And the same thing, like it's because you can see the changing the daylighting performance at this corner when the window sizes are changing. I just made it animated that you can see, you can get the whole concept. And this would be the final result. So the grayed out solutions are the very first round, and it's step by step it's improving. So the first generation would be spread out through the all over the space. The second round it gathers here. The third round, and the yellow dots with green lines around them are the final solutions. And the ideal place would be here, which this is negative daylighting. So when it goes this direction means the better daylighting, and goes this direction is better energy. So our ideal place would be this corner, but there is no solution that has like perfect daylighting and perfect energy. But overall, you can see that there are some solutions that you can choose as a designer later based on other specifications of the project. You can go with this solution, which has the best daylighting but not very good energy performance. You can go the reverse with the best energy but not very good daylighting performance, or something in between. You can include aesthetics and other things by navigating through in Revit and see how they look in Revit. And I just connected with different looks of the model that it helps you. Like this one doesn't have any windows, so it doesn't make sense. So you don't go with that. This one has like very large windows, and like you can choose whatever that matches your project. Okay. Any questions? Sorry, too much information for.
Can you remind where one can get additional information on these tutorials?
Yeah. I think the best would be sending out an email, because it's on university website. It's not very straightforward, but it's BIM, like BIM for building information modeling -SIM for simulation.org and Optimo, and this page is getting started, and it has the videos here.
I have a question, and I'm not familiar with Dynamo, so excuse me if it doesn't make any sense, but your approach seems to favor maybe less perfect solutions that, like the example of the depression, that have a wider span than sort of a narrower solution that may be deeper, because the chances of it being found in the first iteration is smaller. So it seems to favor maybe less perfect, but sort of broader solutions. Is that
this song?
Yeah. Do you have sort of a fail-safe for that? Do you know what I mean? You get.
I didn't get the last one. Do I have one for it?
Well, how do you overcome that?
Oh, so that's the open thing in optimization process. If you don't have any idea where to start, you'll have a hard time, because you don't know. You remember for the points, I started between the range from 0 to 300. If I have more information on my problem, I know that they're focused at this part, so I reduce that range. It quickly goes to the solution. But if I don't know anything, I need to leave it open, so it doesn't fall into a local optimum. We want to find the global optimum, right? But if I range it at this point and our global is here, we never get that, because we are limiting it to this location. But if I know that my global optimum is here, I just focus at this part and quickly get to the solution. But if you don't have any idea, you need to make it that.
Yeah.
But you're actually onto a really good issue. Part of what's going to come up, I was talking, about this before the class was ready. It's like we're getting to this notion of multi-layers of optimization. Maybe we start with the very broad and kind of figure out what neighborhood we should be looking in, and then move into a second phase where you get even finer type of analysis that gets more precise and gets you those very deep solutions in that local neighborhood. So, we're not quite there yet, but I think that's where the next phase will be going.
Feel free to add it.
Exactly.
It's open.
One more thing that I forgot to show you, just in Dynamo when you want to add a package, most probably you know it already, but you can go here to search for package. It takes like a few seconds to get synced with the source, but when it does, you just search for Optimo, and it brings it up. You can see it here, and I think the information for the website also you can find it here. So this is also a good place to go and look for more information.
Optimo is the one?
That one?
Optimo.
No, I saw it today. It seems that it's underdeveloped, but it's not changed for 2-3 months. I didn't try it. No, it's not me.
Somebody grouped up your name?
Let's change the O to an A.
Oh, she's a female.
Oh, but he's a god. Ahmed is the god.
You put them together.
Yeah, I mean, cool.
Any other questions?
So I know about Grasshopper. So Grasshopper has some basic function for you, but for Dynamo we have to create function ourselves. Or is there a basic function?
For you mean for Galapagos? That is for
No,
optimization or for?
Yeah, for Optimo. Do we have to create function ourselves?
It depends. If you want to do like a complex thing, you need to create a function for yourself. But if it's something very simple and the node is available in Dynamo, you don't need to create. Let's say you want to have the area of a floor plan in Revit as your function, and there is a node in Dynamo that calculates the floor plan area. You don't need to create that function for yourself. But if you want to do like amount of sunlight on a TV or something, and there is no specific node in Dynamo that does that, you need to create it for yourself. So it depends what you want to do and what's existing.
So can you guys kind of introduce some basic function that Optimo has? Maybe not today.
Basic functions that
Yeah.
if you look at the examples, the examples start from very basic to get more complex. So, and then I think your class video was very good to get a lot of stuff in there. Yeah, Glenn is going to show you a class website that has all these examples recorded, and it's available on YouTube. Like it's about like an hour or so.
There's a bunch of sessions. There's like 22-hour sessions, like 40 hours of video out there.
Okay.
But it's like sort of broken into discrete examples. Kind of start from zero and kind of build up.
All right, so
Thank you.
thank you very much.
Sorry, I have to leave now, but I know Glenn knows more than me, honestly. So he used Optimo right away after I released it, and I was very surprised that someone can go that deep in few days. So he knows way more than me. So if you have a question, your hard question,
Thank you.
Right, so the second part of this presentation will feature Glenn.
Great.
And we'll pass you the presenter.
Okay, let me go for that. Oops, did I hit it or not? I don't think I did. I'll share my desktop. There it is. Share my desktop. Okay, there we are. And there we are. Okay, super. Let me get this thing going over here.
Okay, so hey there, thank you for having me. My name's Glenn Katz. I teach down at Stanford, a group of civil engineering graduate students and undergrads who are just sort of interested in all aspects of AEC. And part of what we do down there is, use a lot of the Autodesk BIM tools. I've been teaching a BIM class and a systems integration class for quite a while. We started teaching some of the Dynamo tools to kind of start looking at parametric design and optimization a couple of years ago when it got introduced. And it's definitely something that keeps on getting much stronger. Really, every couple of months, another major release seems to come out that introduces a whole lot of new features to what we do. So I was very happy to go ahead and stumble across the Optimo material because it took what we were able to do with optimization really to the next level very, very quickly. But what I wanted to do today is kind of show you some examples of kind of what we did before Optimo. There's a couple of basic approaches to how you can just get started with optimization very simply, just using some of the built-in nodes, and then show you kind of how we could extend Optimo. And that's one of the real beauties of Dynamo is that it's very extensible. You can just kind of keep on adding pieces to it, adding your own custom nodes, publishing those, and there's really a whole really incredible open source community that's building up around it. So it's a pretty good starting point. Okay, so what I'm going to start with is just some examples of kind of some simple optimization stuff we've worked on. A lot of what we do, as an example of what you can do with optimization is look at different building forms and think about just how favorable those building forms are for different reasons. In this case, what I'm looking at is kind of the notion of a building form which is actually somewhat similar to the Shanghai Tower. It's sort of driven by that. That we're going to sort of twist a little bit and kind of experiment with the form and really start thinking about the favorability of some of the surfaces. Could be relative to anything. In this case, we're looking at sun directness. So the whole idea of how much sun's hitting each of the different surfaces. And there's some very basic geometric stuff you can do right within Dynamo. In this case, we were doing some stuff with just vectors from the normals to the different surface panels to the sun and how direct those things were. Turns out there's some really good new nodes that are being re-added into the world that'll actually let us extend that to kind of compute real insolation values over different periods of time. So if you really wanted to consider the amount of energy hitting that plane and the potential for either collection or what you have to resist, they're available. But it starts out with simple things like this. I got a simple little parametric object there, and this little object really doesn't have all that many things going on, but one thing that it does have at the top is this notion of what the rotation is. I have this thing set up so that, if I put in a rotation, let's see if it'll twist around a little bit. There, it'll twist around, something like that. And what we wanted to look at was just this whole notion of, as you start twisting and reshaping the tower, either making it taller, shorter, twisting it around, just how favorable some of the different surfaces could be. What's sort of interesting about this shape is, as you start twisting the tower, some of the surfaces start going into the dark, but other surfaces start coming around into the light. So it's a little bit odd about just exactly what the perfect shape of that tower should be if you want to try to maximize the sun directness. So we went ahead and sort of just applied Dynamo to that. And it's actually a pretty easy thing. Let me actually comment. All the examples I'll show today are out there for you. So you can play with them on your own. And where you actually find them, if you are interested, is here. Okay, this is a site I maintain called BIMtopia. It's just a big collection of all sorts of videos from teaching and answers to a bazillion different questions people have had from the various BIM classes. And the whole parametric design class is 120C, 220C. All the class sessions are out here. And if you go to any of them, I think some of the Dynamo stuff happens here towards the end. Like evaluating design options for solar potential. You'll pop out there. A little bug in my back-end coding. I got to get that fixed. It'll tell you, it'll give you mind maps and slides from what's going on with the session. It'll also have videos from the session, as well as all the data sets. So you can download any of that stuff and play around. So BIMtopia is just sort of a good site for finding a lot of information out, or kind of finding a lot of resource. So anyway, we have this example that's hanging around. We wanted to apply Dynamo, and it's actually pretty easy to do. As we go through and start thinking about how we can think about what optimal forms are, there are a couple of big tools that are available and built right in to Dynamo. And the most common ones, the ones you'll probably get the most use out of, are actually, let's go ahead and I'll open this one. It's a lot of examples. They're sort of building up from scratch. The way all these things are structured, I put all the nodes out there, the way we do most things in class is kind of build up from a very small base and continue to add layers of complexity and one step at a time. So there's usually like 5 or 6 steps to kind of get to the final result, which is good if you're trying to learn it, because then you have a chance not to get overwhelmed by the complexity. What happens in this one is we're going to go ahead and play around with twisting that tower. We use the basic construct that's built in of what's called a list map. And a list map is actually a really good way to start with your optimization. List maps look like this. You take a whole series of values and you feed them to one of these functions. In our case, we had a function that was, as we twisted the tower, it was going to report back some average of the directness of the sun values, something like that. So we're going to go through and feed it an exhaustive list. Now, that's kind of easy, but it's actually kind of inefficient at the same time, because as we're going to go through and feed it this list, it'll start at 0, then it'll do 5, then it'll do 10, then it'll 15. It'll march on down that list. But if you have a large number of points to compute, especially if you have some big two-dimensional XY space, it can take a really long time. So exhaustive, good from the standpoint of making sure you don't miss anything, okay, but pretty inefficient as a way to do it. But hey, it was available and easy to work with, so we started there. So the idea here is we have, some values for just what the twist could be. I went from a twist of 10 to a twist of 40. What I'm doing is I'm feeding them into some custom code block, and you can write your own or work with the ones that are built in there. This one actually does some pretty simple stuff. What it really does is just take some value I feed it, sets the parameter called twist to that value, lets Revit or update itself, and then reads the value back. You know, some value that we're computing it, whether it's the area, the volume, or something. Revit's a really good calculator. Okay, and that's what we're really using it for here, is just running through and doing a lot of calculation with it. Okay, so you take this thing and you say, great, let's go ahead and run it. I'll just run it from, 10 to 40. We'll say run, and you'll see what happens to the little tower there in the background. If the demo gods are helping, it'll kind of evaluate it for 1 degree of twist. It'll start rotating to another degree of twist. Start rotating to another degree of twist. Every time you can sort of watch it do the refresh. It's basically updating the model. And it's important that we do update the model, because it's really the model updating that's giving us the new values. We have to update the model so we can evaluate what's happening with the sun directness. So super. It pops through and does this. At the tail end of all this, I'm going to get a whole series of values that I can write out to a CSV file. Okay, or what I actually sort of prefer is to take them to an Excel file, and there's some really good functions built right into Dynamo to take it either way very easily. So you come on out here, you open the Excel file, see if I can get it. Oh, it's up there, it's shrunken. Okay, I still had an old version hanging around in there, but for this sort of tower, for all the different degrees of twist, I have this notion of a gross surface area, a gross floor area, and then some ratings of the average sun directness, as well as I'm actually sort of calculating some sort of ratios between things. So it's pretty easy to get numbers you want. The trick is what you do with those numbers. Okay, and that's always the hard part of any of these optimization schemes, is that, especially if you're considering more than a single item, you don't get a single answer. You tend to get a frontier, some Pareto frontier of the range of options, and you got to figure out where you want to be on that frontier. But at least you know the way you've defined your functions, your evaluation functions, they're all theoretically equally attractive. Okay, so it's a starting point. But list mapping is a great way to get starting, and it's pretty easy. You set up a function that just has some sort of input to a variable. It reports some value out, and then you just run it through that entire list. And it's good, exhaustive, but slow. Okay, so if you're interested in kind of seeing examples of list mapping, okay, out there on the website, I could kind of summarize where these different examples were. In session 14, we talked about a lot about that and how you could do that. We did this in 2 different ways. One is looking at the issue of kind of the directness of the sun. Another variation that was really easy to do was to say, what if we instead were looking at the issue of the tower twisting and deforming relative to some target that we wanted to see, some very attractive landmark. You're in New York City and you want to see the Statue of Liberty or some bridge or something like that. And it's really the same kind of math. It's just going through and computing vectors from the surfaces and how direct that is. It's just pretty easy to set up. So if you're interested in that, it's real easy to get started. Okay, so that was the start of this adventure. Now, list mapping is actually kind of an okay way to go through things, but there's some things that are sort of dissatisfying about it. So we went after kind of the next way you can sort of approach optimizing, and that's using what's called a while loop. Okay, and looping has some advantages, but also some complexity to it. Looping works like this. That is, we're again going to start with some value. I'm going to start with a degree of 10, some sort of twist. Okay, I'm going to say, hey, am I there yet? Okay, it's sort of based on the am I there yet? Okay, so tries to figure out, are you either there reaching a value, or you're at a value that's lower than the adjacent values or lower by some threshold, but you're sort of defining where you want to stop based on some criteria. So you go marching along to 10, am I there yet? 20, am I there yet? 30, am I there yet? And it's actually pretty good, because you don't have to go to 200. If the answer is at 50, you'll pretty much stop at 50. Although the weird thing about Dynamo, just kind of the way this piece is implemented, you actually don't figure out you're there until you sort of figure out you're one step too far. You go to the part where it breaks, and then you have to back up one. But that's okay. There's easy ways to work around that. So an example of what that looks like is, we can open up a different one. A little while loop. Now, this example is going to seem so mundane, you're going to wonder why we bother doing it. Let me sort of explain about students and maybe people in general, like why you do things like this. The danger with all this stuff is that it is so easy to get lost in the complexity. It's often really easy to not really understand whether you have the right answer or not. You have some number, it looks like a good number, but if you're testing on a really hard problem, you may not really have a good intuitive feel of whether you're even right or wrong or heading in the right direction. So one thing I do with the students all the time is we really just go through and just start with very basic things. I got a little rectangular box. It's like 10 by 10. It's a certain height. I know what the volume of that box is. I could compute the volume of that box myself, but I want to make sure the computer can compute it. Because if I can get the logic to work to do the right thing and confirm that it's doing it, then I can extend the example to be something much more complex. So I highly recommend that when doing this stuff, because it's easy to get lost in the complexity. So I'll go over to, where did it go? Capturing images. Come back over here. This is actually not a bad little script here. In some ways it's very similar. What I'm doing here is I'm starting, what I'm going to do is take a look at this little box, and I'm going to say, hey, we're going to start by giving it a height. I'm going to start it at 1. That's what I'm saying over here. And I'm going to, intriguing. Over here, that's scary. Increment it by 2 every time, and what I'm going to do is keep on going. I'm going to set some sort of criteria. In my case, I'm going to go for the gross volume being 1,700. Or I can make it 1,400 or whatever I want. I just basically have some sort of test and some sort of criteria, and I'm going to let it rip. So here's what it looks like. Kind of grows, it's testing, it's kind of doing okay. It gets to the point there, it's stopped with a gross volume of, ooh, that's special, 1,300. Okay, didn't quite hit 1,400. It won't hit 1,400 because I'm incrementing by 2, okay? So if I changed it to another value like 17 or went by 3s or something like that, I'd actually hit the right value. But it's actually pretty good at going through and going just as far as it needs to go and no further. And there's a real efficiency to that when you're trying to do this optimization. So how I did this, or where we use this sort of technology, was it's almost as we're twisting the building around or changing some parameters, if you know you have a target floor area you're trying to achieve for the building, but you're sort of messing around with the overall form, as you twist and deform, you can then say, okay, and grow it up to the target floor area, so no matter what degree of twist, you have the right number of floors to still give you the target floor area. So you can kind of start using these things together. It's a really useful thing, and you can layer them together. You can iterate to a value, and then do a little targeted looping to kind of compensate. Then for the next value in the while, or in the list map, kind of do the while again. Yeah, it all kind of works together. Yeah, you can also build some cool things in here. In this case, it's sort of interesting, you know, I'm sort of biasing this in that I know that I'm below the target value, so it's going to grow up to it. I actually added a little color here to confirm, you know, it's green to show that, you know, I'm sort of within range. But you could also start adding kind of cool little feedback for your designers too that may be helpful. For example, oh, if I was going to say that as opposed to starting low, I actually started high. Let me go ahead and start at like 18 or something like that. So I'm actually starting higher than a valid value right now. Sometimes that happens if you're not really quite sure where the answer is going to be. You know, oops, that looks like it's still, did it come to the right value? Came back to 16. I guess that's, I'm not so good at breaking my own math. Let's do that. Okay, I can start giving some color feedback. So in this case, I'm a little bit over the maximum that could possibly happen. If I went higher, I could even colorize that and give you sort of more severe feedback about really how far off you are. Because as you're doing this optimization, it's good to give visual feedback. In fact, one of the things we did relative to Optimo animated is we tried to build a way in to give you visual feedback about what's going on. Because if it's all just sort of a big black box mystery and you get a bunch of numbers at the end, that's kind of okay. But we're actually pretty good at watching patterns and seeing if the behavior that it's heading towards intuitively matches what we think it should be heading for. So that's where we went next with this. So we list mapped, we while looped, that was all good, but it still wasn't all that efficient in terms of what we really wanted to do. So that's where Optimo kind of came into the picture. So we picked up Mohammed's work with Optimo and started with it and tried to enhance it a little bit. Let me kind of show you what we did. Okay, let me go on out to his minimum points on a surface. Watch out for this. You'll notice I have two versions here, the metric version and the non-metric version. As Dynamo updates itself, one thing I want you to be very careful about is every once in a while the notion of how they handle units changes. And this has come back and bothered us several times in the past. Like about when you put in a number, is it the unit system that you have set up in Revit, or is it indefinitely the metric system, or is it, yeah, it's varied between each of the different major releases, so watch out. Yeah, his example works better in metric. Well, actually you'll see, because I'm going from 0 to 100, he cheated and went 0 to 300 and sort of achieved the same effect. But watch out for that. In terms of different things to watch out for when different releases change, of all the different things, units has been the biggest sort of hidden gotcha that kind of keeps on coming back up. So here's his minimum surface over there. You can sort of see what it looks like there. Okay, and Mohammed's work did something really nice. It, you know, basically set up that well loop. Actually, the whole notion behind Optimo really is great in that it's kind of what I call a scouting approach. The idea is, hey, if I have a big field, you know, 100 miles by 100 miles, and I can't exhaustively go out and kind of find everything, I'm going to send scouts out into the field. And the more scouts I send out, the more likely it is I'm going to actually end up near the good answer. Okay, it's going to take more time, but that's a trade-off. I can choose how many scouts to send out. And every scout's going to report back, hey, I'm a good point, or I'm not a good point. And then the scouts that have kind of good attributes, we're going to send more people over there. And we'll keep on looking in that area of the field a little more closely. So that whole notion is really, it's pretty strong. It works very well for, at least as the first level, kind of figuring out the neighborhood you should be looking in before you start doing something a little more exhaustive. Although the hybrids where it's always going to get interesting. Okay, so his notion was really good. Some of the things that were a little limiting, though, about what his thing did was it goes through and it finds the answer and it gives you the answer, but it's not very transparent about how you got from here to there. His animations show you the individual points, but just out of the box, the example doesn't do that for you right away. So we went ahead and tried just adding a little to it, and it was actually very easy to do. So what's happening over here, see if I can figure out this example, is I went through and did a couple different major steps to it that went through and started with saying, okay, let's draw the points on the surface. That was super. Then let's actually go through, and the way the data values get reported automatically, it's kind of 3 clumps. You have all the x values together, then all the y values together, then all the z values together. Okay, so that doesn't sound very nice. Let's go ahead and just transpose it all and put it all like x, y, z, kind of in a big old table. Super. So we went through and did that. Then we actually went through and took it a little bit further and said, let's go ahead and not just give you the final result, let's show you what's happening at every step of the way so you can see what happened with all the points during iteration 1, what happened to all the points in generation 2 and generation 3, so you can sort of see it. So let's kind of show you that. It's actually very easy to add that in. What we did with all that is really just, it's still his function. You sort of see the same sort of stuff in here. He has this population of 50, that's 50 points. He has one objective. He's evaluating what the z value is. He has x and y's. I'm going from 0 to 90. None of that's changing. All I had to do is add in a couple nodes over here of what's completed on the while loop. So what's happening here in the function, not only am I going to increment, but I'm going to record the results at every time. We're just basically going to write out data every time and capture it and write it to a CSV file. So it looks something like this. We'll go through and run this. Let's see how many iterations we have it set up for right now. Okay, we're going to run it 3 times. That's the number of iterations. I also sort of relay things a little bit. So great. We'll go ahead and say run it. Okay, there is the end point. That's what it looks like after 3 iterations. Okay, let's go ahead and take a look at the data file. See where I put the data file. Hang on here. Record results on loop. Optimo results. Okay, let me find it out here on my desktop. Okay, so here you can start to see what's happening with the points in generation 1, what's happening in the points in generation 2, what's happening in generation 3. Okay, so got a little bit better, but that was still not good enough. I said, what if we could actually just have a snapshot of what the model looks like at every step? Because I kind of respond visually. Let's see those points actually consolidating. So again, extended it just a little bit. We sort of added another node to this that just kind of plots the points every time and then writes those points out. So, hang on, I'm in the wrong space. I need to be over in Dynamo opening that. It's going to look amazingly similar. About the only thing we do here is we add another node that says not only record the results to data file, but export the image every time and put it in some file called results. So what that lets us do is as follows. If I go through and run this, okay, I'll go ahead and run it 5 iterations. You see there's the first generation, second generation. Oh, don't do that to me. Third generation. On the Mac with the geometric parallels, there's goofy stuff that goes on. There's the 5th generation. Okay, I think we're there. So we're getting pretty close. We're not all the way there. But the important thing about this is because we're actually writing it out, even if your machine blanks out on you for a minute, not that it would ever do that, we have, where are the result images? There they are. Okay, just a whole series of different snapshots that kind of show it going from the first to the second to the third to the fourth. So you can actually kind of track what's happening, get a little bit of visual feedback. And for me, that's helpful. I just really like to see it kind of consolidating there. The cool news is that little chunk of code, write out the data, kind of update the model, export the image, perfectly generalizable to any problem. So in the same sense that Mohammed is saying you could put almost any objective function in there that you want to use to evaluate it, you can. It's just, but that little chunk of code, you can borrow it and copy and paste it right into your chunk of Optimo and be using the same thing. And that's the beauty of the whole open source nature of this stuff, is that, I did a little work on the visualization side, and you can take advantage of it for whatever you're trying to do too. So, in Optimo, we started with this sort of basic example there. Let me tell you where we finished with it though, or kept on going with it anyway. This kind of example of these XY points with the Z's, why does it do that? I don't. I get close. It's interesting. It's magic. Either that or I have an aura I don't understand about. Okay. Interesting to move points around, but hey, I want to get back to building shapes and stuff like that. That's what was sort of interesting to me. So we said, well, how could we actually go ahead and use this same approach, or this Optimo approach? Because the type of evaluation I want to do is kind of still the same. It's just, as opposed to a bunch of lists and iterating through lists, I want to use this scouting approach. I want to just sort of set values out there and try different building shapes and all that kind of stuff. So we headed off in this direction. We said, what if we decided to think about buildings as being populations? Okay, so here's my little twisting tower. Okay, this is a population of 3 of the twisting towers, and I can imbue these 3 different twisting towers with different attributes. I can give them different sort of genetic characteristics for the amount of twists, the amount of width in the middle, and evaluate them in some way. So I could evaluate them in terms of sun directness. I could evaluate them in terms of sort of compound criteria, like the total volume enclosed versus the amount of surface area. Okay, I could play all sorts of different games and do all that. And how that works in Dynamo is kicking in over here. Let's just do it right down to there. A lot of ways this looks very much like the other ones do. The only changes that you typically have to make as you're adjusting it to your problem are on the input side. Okay, we're going to say, that's right, yeah, which your population size is. 50 looks awfully high there. I'm going to change that down. But basically, you choose, no, this is the wrong one, I can tell. It's like, that's the points. Hang on, let me go back over here. Point on surface. Oh, it's because I'm looking in the wrong folder. That might make the reason. On the input side, I'm still going to have one objective, but I'm going to have 2 different inputs. And this is what you start getting into with Optimo and all these optimization things. You got to think about how many inputs versus how many evaluation functions. Because you could have many inputs to change and only a single evaluation, or you can have a single input and multiple evaluations, or you can have some hybrid of all those things. And it all sort of mixes right here. The number of objectives is the number of evaluation functions. That time I did touch it. Okay, and that has to match with the number of functions you feed it in just a little bit. These are the different inputs. What I'm doing here is just basically varying the degree of twist from 10 to 300. I'm also varying the radius in the middle from 10 to 400. So I'm kind of playing 2 different games. I'm twisting it, and I'm also making it fat at the same time. And what I was trying to do is actually go through and evaluate some sort of fitness. Let me find it there. Twisting mass. Okay, fitness function. What I'm actually doing here is, edit the custom node. And this is the part you would replace with your own. I really just go ahead and, for every item in the generation, do sort of very similar things. I set a parameter, so in this case I'm going to go through and set the twist, and I'm going to set the width, and then after that I'm going to get some parameters, I'm going to get the area, and I'm going to get the volume and divide the 2 things together. So that's pretty much what my function looks like. All this layers I have to do is just a way of being able to do multiple ones at the same time, to use this function-like functionality to go through and be able to evaluate a whole family of them, as opposed to evaluating a single one. So I kind of tie it all together. Cancel that. Come back over here. Right there. No, it looks like I closed it. Come back in. There we go. Okay. This is a case where I need to update this because one of the things that changed in the latest build was, am I feeding it degrees or am I feeding it radians? So I'll just go ahead and fix that on the fly right here.
In fairness, that changed in March.
That's true. That's true. But you got to keep watching. It just every time's a little bit of a mystery box. Okay, so you go through and run those things. So this is actually, I know it's going to fail after a little bit, but that's okay. I'll give you a sense of what it looks like. Because you got to, at least for this, think of these things as being a family of buildings. You'll see it'll spawn a family. You can sort of see there that it's going to black out for a little bit. Actually, maybe this will run. Surprise me. No? What did it do finally? It should be there. Well, you started to see it going ahead and generating a bunch of different building sizes, but what it does is it feeds in a random amount of twist, a random amount of thickness, and then it iterates through based upon the ones that are best. And what you find out pretty quickly in the whole notion of surface area versus volume is that these big spheroid sort of objects sort of do very, very well. Again, simple example, but I wanted to kind of make sure it sort of did that before I got too far into trying to test something too often odd and interesting. Okay, the last example, and we'll finish up with this one, is just, what if you actually want to consider two different inputs, and there are two different evaluation functions? Do I even have them here? Not sure if I do. Let's go out into the add-ins. Bring up Dynamo again. In terms of thinking about two different inputs, again, you just need, well, in this case I have two different evaluation functions. I'll also put it that way. I've had two different inputs in the last one there. Come back here. Multiple objectives. So here I'm just looking for a couple of different things I can go through and evaluate based on some shapes. What I'm doing in this example is actually just changing like a basic little rectangular building, and I'm changing sort of its width by depth and also the slope of the roof to try and figure out something about, what kind of shape is going to give me the best kind of amount of energy that I can capture from the roof. Should I change the slope, or should I make it a longer building, or what I should do? And this is an example where that insolation example, that solar radiation example, will become very, very handy, because I really want to kind of collect true values, not just kind of play around with directness. But what we do in here, in many ways, it looks very similar. You see what I'm going to do is to change the slope of the roof from 5 to 75. Okay. I'm going to change the width of the building from 100 to 250. The building's sort of related, so as I change the width, it kind of maintains some sort of constant area. You can sort of set up however you want. But there's two objectives in this case. Let me go ahead and fix my degrees to radians, which I should have done in March. That's right. That's fine. I have fun with this. Okay, and in terms of evaluation, there's two different measures, and what am I doing here? If you go digging on into this, what am I doing in measure one? Let's see what measure one is. I'm going to edit the custom node, see what I'm evaluating. What am I pulling out? Get the parameter value, get the parameter value. Can't tell what I'm doing right off in this one. Oh, I'm doing something about the area and kind of computing a cost of the area, and I'm doing something else in terms of the area of the building. But basically, you're going to get two different numbers, and those two different numbers are going to actually give you a whole series of different points that could conceivably be equally attractive along this Pareto frontier. So it's pretty easy to do. It all really comes down to the writing of these functions. So the cool news out of all this is all Mohammed's work you get for free. That just kind of comes and it works, and it just sort of happens in the background. all your work really comes into writing these evaluation functions. But that's kind of fair, because that's really sort of what you're after, is trying to figure out what it is, how to encode what it is that you're trying to drive in the behavior. So, I'd say just overall, Optimo is this like huge win for people who are trying to do something like this, because it just really, it takes a lot of the grunt work out. And the nice thing is it even separates the problem in that if better algorithms for spawning different genetic mutations come along, that can happen in the background, and you can kind of just keep on worrying about what it is you're testing and how you're testing it and evaluating it and making sense of the whole thing. So that's kind of it. Again, if you're interested in any of this stuff, there are lots and lots of video resources and examples. You can download and play with any of this stuff. And we play around with this stuff in class, like at Stanford, like every quarter. So if you're interested and have questions about how you might apply it, just write. It's like my address is on the BIMtopia site. I'd be very happy to kind of like talk with anyone about the problems you're trying to solve. And to some extent, if we could find seeds of things that we could introduce in class and get the students working on, that's all the better for us. Because I think it's one of those areas where we're all kind of working on it together, just trying to figure out how to harness the incredible power of what's in front of us here. Super. Okay, so that's kind of it. Questions? Anything? I'll even try and field Optimo questions, although Mohammed really knows a whole lot more about it. Anything? Okay,
So
not to worry. Yes?
What other tools are there besides this one that assist the AEC industry on optimization that you're aware of? Or is this just the front line?
What is it? This is, I think the most extensible. This gives us the most power to really start customizing it in ways we want. Or, how would I say? Now, it's the most customizable relative to the degree of difficulty or accessibility. There are tools out there that let you get into a lot of custom programming to kind of go through and manipulate a whole lot of cases and, pull values out of robot structural and do all sorts of weird stuff. But you sort of need a degree in programming to do that, where this, I think, keeps us back at the level where most people can kind of get it. At some level, it's just like stringing together Excel functions or something like that. So, I think that's the biggest thing I'd really kind of characterize as. It really sort of pushes the accessibility and the ability to look at stuff like this, down to a place where we can all get at it and share the problem, as opposed to kind of sending it into the back room for IT to work on. Cool.
What other sort of exciting opportunities do you see already, like in the AEC world, for optimization? Like one of the ones that Mohammed showed was like, since it's this perennial problem with energy performance, that you want to make sure that you have enough light, but you don't want all the daylighting to heat up your space so much that you have to introduce a lot of cooling. So like like energy versus daylighting is involves two different simulation engines, which you get the degree in programming to really kind of hook some of those things up.
Yeah.
Do you see other like?
It's the ones that I work on at Stanford is we're doing a lot of work on structural optimization. So it's really trying to go through and look at, it's how to incorporate information that's now available into our thinking about the structure and how to optimize it, not just based on the weight of the structure, because we've been doing that for a long time. We sort of choose member sizes and try and make it small, and theoretically it weighs less, so it's going to cost less. But to actually start incorporating things like real-time data through XML from the steel mills and the manufacturers, so that the availability of a piece, which actually does have a big impact on the cost, and whether it's going to be able to be on site in 3 months or 6 months, or you can start factoring that into the cost and the schedule and getting those things working together, because they're not really independent. So I think that's where I think really the power of Dynamo comes from. It's our ability to kind of start hanging these different things that we've been optimizing or thinking we're optimizing independently into these more comprehensive understandings of how they kind of interconnect. So that's where I think the big change is going to happen here. Cool. Okay. Then I will turn the floor back over to our gracious host.
Thanks.
All right, my pleasure.
All right, so I don't think I have anything else to add. Thank you very much, Professor Katz.
Caesar, can I just add a word about Adam?
Oh, yeah.
Next week about Adam Schindler?
Go for it. Just speak up.
Yeah, so I would just say, our organizing committee, we're trying to come up with really good speakers, especially for the first few sessions. And Adam Sheether, who will be presenting next month remotely from either Australia or Malaysia or somewhere down there, wherever he's moving around, he's one of the sort of big Dynamo power users, and he has written 2 different packages that are pretty popular. One of them is called DynaWorks, and so it's interoperability between Dynamo and Navisworks. So like you can look at clashes in a more automated way, for example, between Revit and Navisworks, and you can use Dynamo as a sort of custom interface. So he'll talk about that one probably. And then the other one, he's using his presentation next month. He's really excited about it, by the way. Is as an own personal deadline to have a gigantic update to his package called UI++. And if you notice in Dynamo, it's very gray. Like it's just there's a lot of gray, and people like Adam have really fixed that quite a bit. So one of the packages he wrote, like use UI++. Things like color pickers and like different sort of input and output devices that he's really he's gotten really good at making himself, and this again because he has access to all the source code, and he's really been able to put all that together, and he's really excited to share a lot of that next month too. So yeah, so that'll be like sort of a big guest presentation. And the other thing is we always try to have if we can like 2 different presentations. So like one thing like. We were thinking, that would be something about what's going on in the community, or some of the Glenn's work. We can look at some of the things that Stanford's doing, and then we also want to do something along the lines of a learning topic too. So if you have ideas that things that you want, like some sort of presentation, we haven't quite figured out yet what the presentation will be next month for the learning topic. But if you want to know more about how to deal with sheets in Revit or something like that, or if you want to know more about how people deal with making funny shapes, like whatever you think is really going to be necessary or useful for you, please send Caesar an email, the SFDUG coordinator, right? Mm-hmm. And we'll definitely try to line something like that up that's useful. Thanks.
Great.
To optimize people's requests to determine the best topic for a future.
You're going to optimize the sandwich selection?
There are no questions online from the people connected on the web, so I think I'll proceed to close the session.
Thank you.
All right. See you next month.
Thank you.